Okay, so welcome everyone to this week's One World Mathematical Physics IAMP seminar. I can see that we have a lot of participants today. So for those of you who are joining us for the first time, this is a regular seminar of IAMP, which is International Association of Mathematical Physics. And I encourage you to join our mailing list to find out more about upcoming seminars. So here you can see in the chat, there is a link to today's slides. And there is also a link to IAMP website and also the email address you can write to if you want to subscribe to our mailing list. So IAMP is the Organization of Mathematical Physics. So also if you want to read more about our activities and about membership, that's also available on the website. It's so great to see so many of you and so many familiar faces. So this talk, as all our talks, is going to be recorded. So you can find the recording later on our YouTube channel and rewatch it, or watch also other talks that have been given in the seminar. And for today's talk, because we have many participants, I encourage you, if you have questions during the talk, please post it on the chat and we'll try to come back to it as soon as possible. If there is something absolutely urgent that cannot wait, you can ask questions during the talk, but please be mindful that there are many of us and we want to make sure that everybody gets their questions answered and that we get to the end of the talk. Okay, so now without further delay, it's my great pleasure to welcome today Edward Witten from Princeton, who is going to talk about algebras and entropies for black holes and de Sitter space. So please, Edward, go ahead.
Well, thank you so much for this invitation and for the introduction. And it's nice to see all of you, at least virtually. So I'm going to start with the general introduction about black holes and thermodynamics, and then a general introduction about the algebras that are important. And then eventually I'll talk about this recent paper on gravity and the cross product, and more recent work with Chandrasekharan and Pennington. But I don't want to assume that you're all experts in all the background, so I will spend a lot of time on the background, both about black holes and about the relevant algebras, although I realize that on each of those topics, there probably are some on the call who are in the audience who are quite expert and perhaps more expert than me. Because of the time constraints, I'll mostly just explain the context rather than the technical details. So the idea of black hole entropy goes back to Jacob Bekenstein, who was inspired by questions from his advisor, John Wheeler, and he asked what the second law of thermodynamics means in the presence of a black hole. The second law usually says that entropy can only increase. But if we toss a cup of tea into a black hole, the entropy seems to disappear. So Bekenstein wanted to generalize the concept of entropy so that the second law would hold even in the presence of a black hole. So he wanted to assign an entropy to the black hole. So one needs a property of a black hole that can only increase. It's not true that the black hole mass always increases. If you have a spinning black hole, its spin can slow down and release a lot of energy. That's even believed to power jets coming from from black holes in active galactic nuclei. So the black hole mass is not the right thing. But there is a quantity that always increases. Stephen Hawking had just proved the area theorem, which says that the area of the horizon of the black hole can only increase. So it was fairly natural for Bekenstein to propose that the entropy of a black hole should be a multiple of the horizon area. For instance, for a Schwarzschild black hole of mass m in asymptotically flat spacetime with the metric that I've written, the horizon is at a radius of 2 gm, so the area is just 4 pi r squared, which comes out to be what I've written here. Since entropy is dimensionless, to relate the entropy of a black hole to area, you need a constant of proportionality with dimensions of area. So Newton's constant provides such a constant. So this is the Planck length, its square is the Planck area in 4 dimensions. So Bekenstein's formula for the entropy was what I've written here, where the constant 1/4 was not clear in Bekenstein's work and was provided by Stephen Hawking a few years later in a way that I'll explain in a moment. So for a Schwarzschild black hole using the formula for the area we computed a moment ago, this is the entropy. And although I usually set h bar to 1, I've included it here because it helps explain why black hole entropy is so big. For example, a black hole with the mass of the sun has roughly 10 to the 20 times the entropy of the actual sun. So anyway, this was what Bekenstein did. And then he went on to test this idea in a variety of ways. And Bekenstein went on to say something that I haven't written, but I really should have written it, so I'll write it now. He defined a generalized entropy, which is the black hole entropy. Now I will set h bar to 1. So it's A over 4G plus S out. S out is the ordinary entropy of matter and radiation outside a black hole. And he proposed a generalized second law that the generalized entropy is always increasing. So for example, for one simple case, when you toss a cup of tea into the black hole, the entropy of the increase of A over 4G of the black hole is more than the entropy of the tea. So although S out goes down, A over 4G goes up by more. And therefore, the generalized entropy increases when you toss your tea into the black hole. Now, Stephen Hawking supposedly was skeptical of Bekenstein's idea and set out to disprove it by studying the behavior of a quantum field interacting with the black hole. But it turned out that he ended up proving it instead. Now, what I've drawn here is called a Penrose diagram of the black hole. And many of you will be at least have a basic familiarity, but I want to spend just a moment to review what a Penrose diagram is. So first of all, it's a space-time diagram of a black hole with angles suppressed. So only 2 directions are drawn, the important ones, which are time, which runs vertically, and the distance from the center of the black hole runs horizontally. And secondly, the picture has been conformally rescaled in a way that Penrose showed to be very useful. So light rays are at pi over 2 angles to the vertical. Light rays look like this in the picture. So for example, this diagonal black line that I've labeled as the horizon is a light ray. Well, it's the trajectory of a light ray. A light ray outside the horizon will go like that and will escape to this region called future infinity, the black horizontal line at infinity. A light ray behind the horizon will instead end on the singularity. So one important thing about the picture is that light rays travel at pi over 2 angles. And Penrose drew this, conformally rescaled the picture to show the causal relations in a simple way. Another important fact is that, so this black line is labeled future infinity, technically future null infinity, but a physicist making observations is making them up here. So if you're sitting outside the black hole and looking at it, you're living near this little point up here. So in the picture, it looks like a little tiny corner at the end of future infinity, but it goes on for eons and eons. That's where you're living if you spend 1 billion years outside the black hole looking at it. The star that formed the black hole originated at what in this picture looks like this little point down here, but again, there was lots of space out there. So the red region is the region of space-time occupied by the star that eventually collapsed to form a black hole. It ends up at this future singularity, the wiggly line. And the region outside the horizon, well, when we make our observations up here, since light rays can travel, since signals can travel no faster than light, the region the future observer can see up here is all this region outside the horizon. So anyway, that's the basic idea of the Penrose diagram of the black hole. So Hawking ended up proving that Bekenstein was right by finding that quantum mechanically a black hole is not really black, but has a temperature of order h bar. The basic way he saw this is as follows. Measurements that an observer at future infinity can make can be traced back to initial conditions on a Cauchy hypersurface. So it probably would have been better if I'd drawn my Cauchy hypersurface like this to reach out to spatial infinity. But anyway, the important thing is I drew a space-like surface. And if you're living at the future up here, anything you see came from somewhere on this blue surface. So when you're sitting there in the future and looking at the black hole, you're collecting signals that came from somewhere on this blue surface, the Cauchy surface. Of course, it was arbitrary where I drew it. I could have drawn another blue surface to the future or the past of this one. Any Cauchy hypersurface will do for setting initial data. Now, the picture now I've drawn in purple, some lines that are meant to be at a pi/2 angle to the vertical. They represent signals propagating from the Cauchy hypersurface to the observer at infinity who's collecting them. And the observer is looking at the black hole by looking at what comes out along those purple lines. What will the observer see? Well, part of Hawking's insight was that although the full details of exactly what the observer will see depend on the details of the collapsing star, if you ask what the observer will see in the far future after transients die down, there's a universal answer. One reason is that what the observer will see is determined by signals on the Cauchy hypersurface, but we don't care about the part of the Cauchy hypersurface that passed through the collapsing star because that's behind the horizon. The observer doesn't see that signals from there. The portion that the observer does detect signals from is outside the collapsing star and far to the future of where the black hole collapsed, star collapsed. So that region is essentially vacuum. But even more important, the signal that is received very late, which means it's received way up here, originated on the horizon, on the blue Cauchy surface, very close to the horizon. The signal that's received very late originated from very close to the horizon. That means that observations made at late times depend on measurements of the state of the quantum fields at short distances, very close to the vacuum. But every state is equivalent to the vacuum at short distances. So the late time observations of the observer probe the vacuum state near the horizon at short distances. That's why Hawking gets a universal answer, regardless of exactly how the black hole formed. When you observe it at late time, you're just probing the vacuum outside the black hole at short distances. To be a little more quantitative about this, let U be a coordinate function. I've drawn the important part of the initial value surface here. U is a coordinate function that vanishes on the horizon. U is a coordinate function that vanishes on the horizon. And you'll see in a moment, it doesn't matter exactly how we define U. It's 0 on the horizon, it's positive outside. T is the time at which the observer makes the observation outside. To find the relation between U and T, we just solve Einstein's equations for an outgoing null geodesic. And when we do that calculation, we learn that T is the logarithm of 1 over U times a constant. What that formula tells you, you know that if U were negative, the signal never gets to the outside observer. If U is positive, the signal eventually gets to the outside observer. But the time at which that happens diverges as U goes to 0. And that's shown by this formula. As U goes to 0, the time at which you observe the signal goes to infinity logarithmically. So we can solve this equation for U in terms of T. And you see that if you make an observation at late time, it originated from a point on the horizon that's exponentially, a point on the initial value surface that's exponentially close to the horizon. So at late times, U is exponentially small, but T doesn't have to be very large. For example, for a black hole with the mass of the sun, this constant 4gm is a few microseconds. So if T is a millisecond, U is the exponential of minus 100. So after a millisecond, U is fantastically small. Also, du dt is equally small. So a mode observed at infinity will have undergone an exponentially large redshift on its way. So a mode of any given energy E that you observe at a late time originated from a very high energy mode near the horizon. That's why there's a simple answer. A very high energy mode essentially propagates freely along these outgoing null geodesics that were drawn here. So we just, all that's important is the change of coordinates, because a high energy mode here will just travel free stream out along a null geodesic to the observer at infinity. And now we can ask what the observer at infinity measures. The observer at infinity probes the radiation by measuring a quantum field psi of t. The typical observable is a 2-point function. Near the horizon, the typical quantum field has a power-like singularity. I wrote something with a first order singularity, but we could have a pole of some higher order. It won't matter for what I'm about to say. Setting u be a constant times this exponential, we simply change variables from the measurement near the horizon to the measurement at infinity. So this formula at short distances converts to this formula at late times. And the important thing about this formula is that it's anti-periodic in imaginary time. It would have been periodic if I'd assumed a double pole. It's odd under a shift of t by 8 pi gmi. And the anti-periodicity corresponds to a thermal correlation function at a temperature, which is the inverse of the period. That's the Hawking temperature of the black hole. So in other words, a black hole, after transients that depend on how it was created die down, radiates thermally at a temperature 1/8 pi gm. We can now find the entropy using dE equals TdS, where the E is the mass of the black hole and T is 1/8 pi gm. We get this result for ds, so we get that S is 4 pi gm squared. And that is A/4g, where A was the area of the black hole horizon. So this is how Hawking confirms Bekenstein's idea and determined the constant. Not long after Hawking's discovery, Gibbons and Hawking considered another situation with horizons, cosmology rather than black hole physics, and proposed that also the area of a cosmological horizon is a kind of entropy. More specifically, they assigned a temperature and an entropy to the region of de Sitter space accessible to an observer. Here's the metric of de Sitter space. De Sitter space may be a good approximation to what our universe will be in about 10 to the 11 years. It's the maximally symmetric solution of Einstein's equations with a positive cosmological constant. It expands exponentially when t goes to plus or minus infinity. Because of the exponential expansion, in the real world, other galaxies, if they're not gravitationally bound to the Milky Way, which those of the local group are, they'll be out of sight within roughly 10 to the 11 years. They'll be behind the cosmological horizon. Here's a Penrose diagram of de Sitter space, but I won't explain it in as much detail. But I'll just briefly say, again, not light rays are at pi/2 angles to the vertical. The directions depicted are time vertically and space horizontally. In this case, I've drawn an observer's world line, this black horizontal line, and what the observer can see and influence. The observer is in causal contact with the green region, which he can both see, detect signals from, and influence. So other galaxies, well, galaxies will all end up behind the future horizon unless they happen to be gravitationally bound to the observer. And Gibbons and Hawking assigned to this picture an entropy A/4g and a corresponding temperature, which actually had been defined earlier. The meaning of the de Sitter entropy has been a mystery ever since. Many researchers have thought that somehow the entropy A/4g means that the black hole or cosmological horizon can be described by some sort of degrees of freedom that live at its surface, 1 bit or qubit for every 4g of area. For example, in a famous article in 1992, John Wheeler illustrated the idea with this picture. He drew a black hole horizon, he divided it into little cells of area 4g, and he imagined a bit or qubit living on each cell, and he labeled them by a 1 or 0. As I say, the paper was written in 1992, but I tend to believe Wheeler had been drawing that picture for 20 years. He had been Bekenstein's advisor, as I said before. Now, more modern understanding of black hole entropy involves understanding what entropy means in quantum mechanics at a more fundamental level. As a preliminary, we could review entropy classically. Entropy was originally defined in terms of microphysics by Boltzmann. consider a system of n particles in a box with positions x and momenta p. Boltzmann assumed that at a given time, x and p have definite values, even if we don't know them. So he would describe the state of our knowledge by a probability distribution function, a rho of p of x. And Boltzmann and ultimately followers such as Gibbs defined the entropy as the phase space integral of minus rho log rho. So this is a classical formula for entropy. Although if you think about it carefully, you'll see that it has an ill-defined additive constant. That's because dp dx is not dimensionless. So if you rescale the units in which you measure dp dx, you can try to compensate by rescaling rho, but then the logarithm will shift by an additive constant. So this formula really only defined entropy up to an additive constant, and that's actually the right answer classically. Classically, you can't really fix this additive constant. The analog in quantum theory of the classical density matrix, of the classical density rho, is the density matrix rho of a quantum system. It has the property that if O is any operator, the expectation value of O is the trace of O times the density matrix. That's if the system is in a pure state. But the density matrix formalism is also applicable for a system that's not in a pure state. In general, rho is a positive self-adjoint operator of trace 1. If we diagonalize it with eigenvalues lambda j, then the expectation value of O, which is the trace of O times rho, is the sum of lambda I times the expectation value of O in the state I, as if the system is in state I with probability lambda I. And that interpretation makes sense because since rho is non-negative and its trace is 1, the lambda I are non-negative and their sum is 1. So rho is the analog of the probability distribution classically. And that motivates the idea that the von Neumann entropy minus trace rho log rho is the quantum analog of Boltzmann's integral. Well, I think it's really Gibbs's integral, although I wrote Boltzmann's integral. So in the classical limit, the von Neumann entropy goes over to the classical entropy, but it fixes the additive constant that was purely defined classically. But there's a basic difference between the classical and quantum cases. Classically, we believe that x and p have definite values, and we use a distribution function rho because of lack of knowledge. So the entropy too reflects lack of knowledge. Quantum mechanically, if a system is entangled with something else, then a mixed state density matrix rho is the most precise description that quantum mechanics allows. So there's an irreducible fine-grained entropy, even if we know the state as precisely as possible. This has no classical analog. The idea that the Bekenstein and Hawking entropy of a black hole should be understood in terms of this entanglement entropy was apparently first put forward by Raphael Sorkin in 1983. His idea was the following. In a quantum field theory, divide space into two regions, A and B. Now, he's motivated by the idea that B is the region behind the horizon, and A is the region that the outside observer can see. But some remarks are more general and involve an arbitrary division of space into two regions. Let psi be a state of the system. For example, psi might be simply the vacuum state of the whole system in Minkowski space. And then let rho A be the reduced density matrix of the state psi for measurements in region A. We're going to criticize that notion in a little bit and explain its limitations. But let me proceed with the way Sorkin explains it. So Sorkin tried to define a reduced density matrix of the vacuum or any other state in principle for an observer who only makes measurements in part of space, and then tried to calculate the entropy minus the trace of minus rho A log rho A. Well, he found that it's ultraviolet divergent, and the coefficient of leading divergence is proportional to the area A of the boundary between regions A and B. Well, the ultraviolet divergence is not nice, but the fact that the entropy is proportional to the area is nice. Sorkin's idea in modern language was that somehow gravity cuts off the ultraviolet divergence, leaving an entanglement entropy in the vacuum between the two regions. That's the Bekenstein and Hawking entropy A over 4G, where A is the area of the boundary between them. So when he actually calculated without gravity, he got A times an ultraviolet cutoff. His idea was that gravity would replace the cutoff by 1/4G. That actually makes a lot of intuitive sense as it matches two ideas. One is that A/4G is the irreducible entropy of the system for someone who has only access to the region outside the horizon. And two is Wheeler's picture saying that Wheeler says the entropy comes from 1 degree of freedom per unit area. The divergence of the entanglement entropy is proportional to the area because it comes from short wavelength modes near the horizon, as if the density of quantum degrees of freedom that are contributing to the entropy is 1/4G, as in Wheeler's picture. A decade later, there was an incredibly simple and naive but important observation by Susskind and Uglum that strongly supported viewing S out as entanglement entropy. So remember, Bekenstein had defined the generalized entropy, the area over 4G plus the ordinary entropy outside. But what is the ordinary entropy outside? Bekenstein assumed that thermodynamics was valid and that S out was thermodynamic entropy. But thermodynamics isn't valid for an arbitrary quantum state. And Sorkin had defined an entropy just for the vacuum as entanglement entropy. Suppose we interpret S out as the von Neumann entropy for observations outside the black hole horizon. Well, the second term has an ultraviolet divergence that Sorkin noted. But Susskind and Uglum pointed out that also the first term has an ultraviolet divergence involving the relationship between the bare and physical observed Newton's constant G. When I sketched Hawking's derivation of Hawking's effect, the G in those formulas presumably was the classical G, the bare Newton's constant. But when we look at a black hole and try to interpret A/4G as an entropy, we're presumably talking about the physical G that we actually observe. The relation between them has an ultraviolet divergence, just as the outside entropy has an ultraviolet divergence. And Susskind and Uglum showed that those ultraviolet divergences actually have equal and opposite coefficients, and that the divergences cancel. They showed this in an extremely simple way in the one-loop approximation. Later authors have improved it and showed that this really is correct in higher orders also. So Susskind and Uglum showed that the generalized entropy makes more sense than either term does separately. And that's a strong support for interpreting S out as entanglement entropy because it is, or von Neumann entropy of the region outside, because it is von Neumann entropy that when added to A/4G H bar does make sense. So 21st century developments have strongly supported these ideas, but they've left us with plenty of mysteries. In the available time, I'm going to talk about just one aspect of the story. Why is it that entanglement entropy is ill-defined in quantum field theory? So S out has that quadratic divergence that Sorkin pointed out, but well-defined once gravity is included. Another way to say the question is, can we interpret the generalized entropy of Bekenstein as the entropy of something? It's a formula, A/4G plus S out. But in what sense is that generalized entropy really an entropy? We're going to try to give at least a partial answer to the related question. So in what sense is the generalized entropy of Bekenstein really an entropy? And that'll help us understand why S-gen, well, we'll understand, yeah, okay. That'll help us also understand the answer to this question here. First of all, in ordinary quantum mechanics, when one considers the entanglement entropy between two systems A and B, one normally assumes at the start that each system has its own Hilbert space, HA or HB. The combined system then has a tensor product Hilbert space, HA tensor HB. The state in this combined Hilbert space might be a simple tensor product. In that case, systems A and B can separately be described by the pure state psi A and psi B, and there's no entanglement entropy. But more generally, we could have a more general state, and then we say that systems A and B are entangled, and there is a von Neumann entropy of the density matrix of system A or system B. So system A, for example, in this case, for this wave function, has this density matrix, and then it has the von Neumann entropy that we discussed. So the point of this is that in ordinary quantum mechanics, whether a state has non-zero entanglement and entanglement entropy is a property of the state. That's not so for entanglement entropy between different regions in quantum field theory. In quantum field theory, well, the divergence found by Sorkin was an ultraviolet divergence, which means it doesn't depend on the state, because every state looks like the vacuum at short distances. So therefore, in contrast to the situation in ordinary quantum mechanics, in quantum field theory, at least the leading part of the entanglement entropy is independent of the state. So this entanglement is not just a property of the state. The root of the problem, or the cause of it, is that it's not true that there are separate Hilbert spaces HA and HB for the inside and outside regions. There's only a combined Hilbert space H for the whole system. What the separate regions A and B have are not Hilbert spaces HA and HB, but only algebras of observables, which I'll call curly A and curly B. These algebras act on the Hilbert space, so they can be defined as von Neumann algebras, where essentially a von Neumann algebra is an algebra. Well, if you have an algebra of operators on Hilbert space, take the associated bounded operators and close it in a certain sense, and you'll get a von Neumann algebra. So because these algebras of observables act on a Hilbert space, we can think of them as von Neumann algebras. But they're von Neumann algebras of inconvenient kind. Von Neumann and Murray had a very general classification of von Neumann algebras. First, there were the type 1 algebras, the algebra of all operators on a Hilbert space. In ordinary quantum mechanics, when we discuss the system A, it has the Hilbert space H sub A, and the algebra of observables is the type 1 algebra of all operators on HA. That's of type 1. So if a system is described by a type 1 algebra A, it can have quantum mechanical pure states, namely states in the Hilbert space in which A is the algebra of observables. And then you can define density matrices and entropies in the usual way. The other types of von Neumann algebras may be less familiar. A type 2 algebra doesn't have pure states, but there is a notion of density matrix and entropy for a system in which the algebra of observables is of type 2. A type 3 algebra is the worst type. A system whose observables form a type 3 algebra doesn't have pure states and also doesn't have density matrices or entropies. By now, you might anticipate the bad news. As was originally shown by Araki, in quantum field theory, the algebra of observables of a region of space-time is always of type 3. So to a region, one can never associate a pure state or a density matrix or entropy. The type 3 nature of the algebra is the reason for the universal ultraviolet divergence of the entanglement entropy in quantum field theory. So Sorkin simply calculated and got an ultraviolet divergence, but we can trace it back to the type 3 nature of the algebra. However, it turns out that including gravity in a semi-classical way, and this is the main point I want to explain in the rest of the talk, changes the picture. At least in the case of the black hole or de Sitter space, including gravity at a semi-classical level changes the algebra of the region outside the horizon from type 3 to type 2. I don't know what would happen if one could include gravity exactly, and I also don't know for sure whether there's a similar answer in more general spacetimes with horizons, although I hope that there is. But at least for the black hole and de Sitter space, when gravity is turned on semi-classically, the region outside the horizon is described by an algebra in which the notion of entropy is well defined, although there's no notion of a quantum mechanical microstate. And there, I should also say there's also an arbitrary additive constant in entropy for such an algebra, like in entropy in classical physics. So I'll explain this assertion that the algebra becomes of type 2 in the rest of the talk, but we can interpret that as a somewhat abstract answer to the question of why, including gravity, suddenly enabled us to convert the ill-defined divergent S out into the better defined generalized entropy of Bekenstein and Hawking. But to understand how this works, we need to understand something about von Neumann algebras of type 2 or type 3. My plan for this talk may have been too ambitious and causing me to rush too much, but I didn't want to assume you were all familiar with black hole thermodynamics, so I reviewed Bekenstein's idea and tried to sketch Hawking's calculation in the simplest way I could. And likewise, I don't want to assume everyone's familiar with von Neumann algebras of type 2 and type 3, so I'm going to give a short explanation to what they are. They can be most simply described as the algebras that act on certain thermal systems. So I'll explain how that works. So a thermal system, well, okay, I should say for finitely many degrees of freedom. Let me just say a finite thermal system with Hamiltonian H and inverse temperature beta has a density matrix, which you can simply define as 1 over z times e to the minus beta h, acting on the Hilbert space of the system, where the constant z is such that the trace is 1. Now, the trouble with this formula is that for an infinite system, this formula doesn't really work, because usually for an infinite system, z would be infinite. And if you try to make sense of the sum over states in the thermal ensemble, in infinite volume, there would be uncountably many typical states, because thermal fluctuations would go off to infinity. And you don't usually want to work with an uncountable set of physical states. So the Thermophile double was introduced by Haag, Winnick, and Hugenholtz, I think, in the 60s as a way to describe the large volume limit of the thermal ensemble directly in a Hilbert space. Roughly speaking, the Thermophile double is a pure state of a larger system with density matrix, the thermal density matrix. So to define it for a finite system, you simply take a second copy of the original system. Then if psi I are the eigenstates of the Hamiltonian with energies EI, the Thermophile double is described by this explicit formula for a pure state. So it's 1 over the square root of z times the sum over all eigenstates of the Hamiltonian. And it's chosen so that the corresponding density matrix is the thermal density matrix, 1 over z times e to the minus beta h. We've chosen this so precisely so that the expectation value of any operator that only acts on system A on the first copy in this state is the same as the thermal expectation value. Now, the trouble with this formula is that for an infinite system, it's not well defined. Z is infinite, but also the sum would have uncountably many terms. And we don't really want to deal with an a non-separable Hilbert space that would have that uncountable set of states. So what one does is one takes this formula. Okay, this formula can serve as the definition of the Thermophile double state for a finite system. But in the thermodynamic limit, one instead observes that a state with this property, characterized by this property, has a thermodynamic limit, although the formula isn't really good in the thermodynamic limit. So in the thermodynamic limit, we don't really define the Thermophile double state by this formula, but we do define a state and a Hilbert space containing that state in which this formula is true. So what happens that funny things happen to the algebra of observables in the thermodynamic limit, and that's where algebras of type 2 and type 3 come in. So let's first consider the simplest Hamiltonian of all, which is 0. So we consider a system with n qubits with Hamiltonian 0. The partition function of that system is simply the number of states, which is 2 to the n. And the Thermophile double is very simple because the energies are all 0. So the Thermophile double is just a completely entangled state of n qubits of system A with n other qubits of system B. It's simply the sum over all states of system A times system B divided by a constant to make the state normalized. So let A and B be operators that act only in the first k spins of system A for some k less than n. And define a function f of A, which is the expectation value of A in the state psi. Well, you can see that, first of all, f of 1 is 1 because the state was normalized. And you can also see that f of AB is equal to f of BA. You might have to think about it a little bit. If you turn the ket here into a bra, then this density matrix would look like the unit matrix. And the expectation value of an operator in the state would look like the trace of the unit matrix times the operator. And then after a little while, you'll discover that f of AB equals f of BA. And one more important fact is that this function is well defined as soon as n is bigger than k, and it's independent of n. So if you have any operator that acts on k spins, and you define the Thermophile double state for any larger set of spins, you get the same answer regardless of how many spins there were. So the function f of A has a thermodynamic limit. It's also positive. F of A dagger is positive for any non-zero A. So far, we've defined F on the whole algebra A naught of all operators that act on only finitely many qubits of system A. By taking the closure of A naught in von Neumann sense, which means we allow certain operators that can act on any number k of qubits, but with matrix elements that decay rapidly for large k. Anyway, a certain closure of A naught is a von Neumann algebra A, still with the function f of A that has the same properties I've stated. Since f of AB equals f of BA, this function is usually called a trace. But it's not the trace of A in any Hilbert space representation. It's more like a renormalized trace with an infinite factor removed. Of course, there's a more elementary example you all know of infinite dimensional algebra with a kind of trace. That's the type 1 algebra B of all operators on infinite dimensional Hilbert space H. It has a trace, but the trace isn't defined for all operators, only for those that are trace class. For example, the identity element doesn't have a trace unless you want to allow infinity as a possible value of the trace. By contrast, from the infinite system of qubits with Hamiltonian 0, we constructed an algebra in which literally every element has a trace. So it's essentially new. In fact, it's the simplest example of a type 2 algebra. It's said to be of type 2-1. It was constructed in essentially the way I just explained by Murray and von Neumann. If A is this type 2-1 algebra and B is the type 1 algebra of all operators in an infinite dimensional Hilbert space, we can make a third type of algebra that's simply their tensor product. It still has a trace because each factor does, but the trace isn't defined for all elements because the factor B did not have that property. So this is yet another algebra, which is said to be of type 2 infinity. It turns out that in applications, A and C are the important types of type 2 algebras. C is related to the black hole and A is related to de Sitter space. Now, this was the Thermophile double of a 0 Hamiltonian, but the Thermophile double of almost anything else leads to an algebra of type 3 in the thermodynamic limit. The simplest Hamiltonian that isn't 0 is a sum of single qubit operators. For example, take this particular single qubit operator. Then at inverse temperature beta, you could consider a pair of spins with this Hamiltonian. Well, the Thermophile double for a single qubit would be given by this entangled state of 2 qubits, where the 2 qubits are fully entangled in the sense that the density matrix is invertible, but they're not maximally entangled. The density matrix is not a multiple of the identity. We can still define a Thermophile double state for a system of n qubits by entangling each qubit pair in the state just mentioned, the state I've written here. And then we can define the function f of a as before. And as before, it has a thermodynamic limit. And that is a good arena to study quantum statistical mechanics and the thermodynamic limit in a nice Hilbert space that contains this state. But there's one big difference, was that it's no longer true that f of AB equals f of BA. So for n going to infinity, we can define an algebra A naught consisting of operators that act on any finite set of qubits. We can again complete it, but now the completion gives a von Neumann algebra of type 3. First constructed in this way by Powers and then generalized by Araki and Wood. Algebras of type 2 or type 3 do not have an irreducible representation in a Hilbert space. Whenever such an algebra acts on a Hilbert space H, it always commutes with another algebra of the same type. For example, we constructed type 2 and type 3 algebras to act as algebras on the A part of a bipartite system AB in the Thermophile double. So in that construction, they commute with an identical algebra that acts on the other copy. But that's the typical state of affairs. Now, what's the important difference between a type 2 and a type algebra and a type 3 algebra? The important difference is that a type 2 algebra has a trace and a type 3 algebra does not. Moreover, in a type 2 algebra, the trace is non-degenerate in the sense that the bilinear function given by the trace of AB is non-degenerate and positive definite. That follows from our earlier result here. Well, I'm stating this for simplicity for type 2.1. It's type 2 infinity is a little more complicated. But roughly, if f of a is any linear function of an element of the algebra, it's the trace of a times some element of the algebra, just because of the fact that the trace is a non-degenerate bilinear form. Now let's go back to the situation considered by Sorkin. So we consider some state of the whole universe. Suppose it were true that in physics, in region A is described by a type 2 algebra, curly A. In ordinary quantum field theory, that's false, as I've told you. The algebra is type 3. But suppose it were really of type 2. Then the linear function that takes an operator to the excitation value in the state psi. Well, I just told you that any linear function is the trace of A times something. So this linear function would be the trace of A times rho A for some element rho A of the algebra. If the algebra were of type 1, we'd use that condition. Well, for type 1, we have such a condition, and we use it to define the density matrix rho A of state A for measurements in the subsystem A. So if we had the same condition for type 2, it makes sense to call rho A the density matrix, also in the type 2 situation. So for a type 2 algebra, but not for a state of a type 2 algebra, but not for type 3, density matrices are a meaningful notion. Once we have density matrices, we can also define entropies. So entropies are also meaningful for type 2 algebras, as was actually possibly first discussed by Irving Siegel in around 1960. So if the region outside the horizon is described by a type 2 algebra, then we can define an entropy for this region. Now, I've already explained that in ordinary quantum field theory, the algebras of regions are type 3. But it turns out that when we include gravity, things are different. Gravitational effects, even for very weak coupling, convert the type 3 algebras into type 2 algebras. The mathematical mechanisms that lead to this are quite simple and have long been known by operator theorists. What's new is only that these mechanisms are actually implemented by perturbative gravity in the field of a black hole or de Sitter space. The details are a little different in the two cases, and I only have time for very brief explanations, although if there are questions, we can possibly go into more technical detail later. But I'll give a very schematic explanation. Well, actually, in So I wrote a paper on the black hole case, and then there's forthcoming work, as I said, with Pennington and Chandrasekharan on the de Sitter case. And in my paper on the black hole case, I considered a black hole an anti-de Sitter space. But you might be more familiar with Schwarzschild black holes in asymptotically flat spacetime. And it turns out that the construction also works in the asymptotically flat case. So what I've drawn here is the Penrose diagram of a Schwarzschild black hole in asymptotically flat spacetime, as originally discovered by Kruskal, Sakaris, and others. The black hole is a wormhole that connects two asymptotically flat universes, which are our two systems A and B. So we're perhaps living in this region, but in a maximal extension of the Schwarzschild solution behind the horizon, there's a second system B. Now, we could also consider a black hole that forms from collapse. The second region wouldn't exist. We'd still get a type 2 algebra after a similar but slightly lengthier explanation. But it's easiest to explain for the idealized case of the maximally extended spacetime, where the two regions are simply the two asymptotically flat worlds, A and B. What is shown in gray are the regions behind the horizons, and these curved lines are the future and past singularities. So if you're in the gray region, then even going at the speed of light, which means, as I said before, at a pi/2 angle to the vertical, you won't be able to escape. You'll end up at the future singularity. You'd have to go at an angle bigger than pi/2 to escape to regions A or B. So here I've drawn it again a little bit smaller. Now, in low energy effective field theory, we'd construct a Hilbert space H0 for the black hole spacetime. How would we do that? Well, we would take an initial value surface, a Cauchy hypersurface, all the way through the wormhole. And then we take small fluctuations of the quantum fields on that surface, and we'd quantize them and we'd get a Hilbert space. This Hilbert space is acted on by algebras A and B of operators on the left and right. Two important operators are the ADM energies, H right and H left, the energies measured at infinity on the right or left sides. Another important operator, the space-time, has a killing vector field, which generates time translations that go forward on the right and backward on the left. It's generated by a bulk operator, which I've called little h. And there's a relation between them. Little h is the inverse Hawking temperature times the difference between the two boundary ADM energies. There's a subtlety, however, about constructing the Hilbert space of the bulk quantum fields in the case of gravity. So first of all, you can expand the metric around the background Schwarzschild solution. I've called G0 the background Schwarzschild solution, and I've called G the metric, H is the perturbation. And then what you do is that in the quadratic approximation, or in perturbation theory, beyond the quadratic approximation if you're more ambitious, but the quadratic approximation is enough to illustrate the point. You treat H as an ordinary quantum field and construct an algebra A0 of gauge invariant observables. The basic such observable is the linearized Riemann tensor. So the contribution of gravity to the right algebra A0 is generated by functions of the linearized Riemann tensor. This algebra A0 limited, well, where we consider only functions that live outside the horizon. What we're going to get is a type 3 algebra. If we consider functions of the linearized Riemann tensor in region A, we'll get a type 3 algebra and we won't be able to define entropy, we'll see. But the algebra A0 and the Hilbert space H0 are not large enough to describe the physics we want. One operator is missing in A0 and one mode is missing in H0. The operator missing in A0, but part of the physics on the right side, is the ADM energy HR, measured at infinity. It cannot be defined in terms of the linearized Riemann tensor. It's not part of the algebra A0 that's generated by R mu alpha beta. Likewise, the mode generated by H of R is not part of the Hilbert space H0 on which the algebra A0 acts. The mode generated by H right is locally pure gauge. It's generated by a vector field V that's 0 on the left boundary and agrees with d by dt on the right boundary. So it's a non-trivial deformation of the geometry if you consider that the observer at infinity who's making measurements has a zero of time. You can measure it by some operator, but you can't measure it by the algebra A0 of the small perturbations. So the correct Hilbert space is not the one that you would construct if you treat gravity like any quantum field. The correct Hilbert space has one more mode. It's the Hilbert space of small fluctuations centered with L2 of R, where L2 of R consists of functions of a new variable x, or equivalently the canonical momentum. And when you have this larger Hilbert space, HR can act. It acts as multiplication by this new operator, plus something that generates time translations of what you already had, roughly because H right is the time translation operator. So a better perturbative approximation to the correct Hilbert space and the correct algebra is to include one more degree of freedom in defining the Hilbert space and one more operator in defining the algebra. It might not sound like much because we had infinitely many modes that were quantized to get H0, and we've just added one of them. Likewise, we had a type 3 algebra with infinitely many generators, and we've only added one more generator. So what I've written here just summarizes what HR is. It acts on the new mode and also the old ones by time translations. So what we've learned is that the difference between gravity and ordinary quantum field theory is that compared to ordinary quantum field theory, we have one more mode and one more operator. In mathematical terms, we've discovered something called the cross product of the algebra A0 by a one parameter automorphism group generated in this case by H over beta. This automorphism group is actually, in this particular case, assuming that is actually the modular automorphism group of the Hartle-Hawking equilibrium state of the black hole, according to famous results of these people. Now, the modular automorphism group, the cross product by the modular automorphism group is extremely important in the theory of von Neumann algebras. Physicists studying entropy are not the only people who have trouble with type 3 algebras. Type 3 algebras are more difficult to understand mathematically than type 2 algebras. But what Kohn and Takasaki did roughly half a century ago was to discover that this little perturbation of the type 3 algebra converts it to a type 2 algebra. And type 2 algebras were known to be more tractable. So the theory of type 3 algebras was developed by using precisely the construction that it turns out gravity actually gives us at the perturbative level. So in particular, Kohn and Takasaki discovered that the algebra extended with one more mode in the Hilbert space and one more generator of the algebra is actually of type 2 infinity. In particular, it has a trace in a notion of density matrix or entropy. You can be rather concrete about the definition of the trace, although I won't write the proof that it is a trace. You can read it. Well, it goes back to Kohn and Takasaki, but you can read a simple account for physicists in my paper. Since A is generated by A0 together with bounded functions of one more generator, a rather general element of A, which I'll call A hat, is an integral over U. Well, a bounded function, you could Fourier transform it. So you have e to the IU for real U times the new generator. That's an example of a bounded function. Then you integrate over U with a weight that's a function, an operator valued function of U. It could be an operator valued distribution, but if it's actually an operator valued function, then we can define, this should be A hat here, sorry. Then we can compute then we can write this formula for the trace of A hat. And you can show that it's a trace for a large class of functions A of U. It behaves as a trace. So that explicitly shows the fact, which I think is pretty startling, that adding one more generator and one more, adding one more generator, one more degree of freedom in the Hilbert space and one more generator of the algebra brings a trace into being. And therefore, with gravity included, for the black hole, there's going to be a meaningful notion of entropy. And you can show that up to an undefined additive constant, which is independent of the state, the entropy agrees with the Bekenstein proposal, or perhaps I should call it the Bekenstein-Sorkin-Susskind-Uglin proposal. Well, I should add Hawking in there too. The Bekenstein proposal is refined by later authors, that the entropy is A over 4G plus the entropy outside. I should also have included Aaron Wall as one of the people who refined it, because what we actually make contact with in the not yet written paper is Wall's further refinement of the Bekenstein proposal as refined by the later other authors that I've mentioned. So if time allows, I'll give an informal explanation in the discussion period of how to make contact with Wall's version of the Bekenstein proposal. But for now, I'm going to go on and discuss the de Sitter case in what I assume is the last few minutes. In fact, the minus last few minutes, because I see it's already 11. So, but I'll just be going on for a few minutes.
Sure, of course.
So something rather similar happens in de Sitter space. So here I've again drawn the setup for de Sitter space. So the square is a Penrose diagram for de Sitter space, but a lot of dimensions have been suppressed. Topologically, this space is R times a sphere, where R labels the time. What's been drawn is time that runs vertically, and space has been compressed to one dimension, which you can think of as the distance from the observer. And distances blow up at the top and bottom of the picture. As Penrose taught us, it's convenient to make a conformal rescaling to map all that to a finite picture, but the time is infinite at this end and minus infinity at the other end. Why can't I advance the slides now? Oh, okay. So the green region, which is the region in causal contact with an observer, is called a static patch. There's a killing vector field of time translations that's future-directed time-like in the static patch. It's past-directed time-like in the opposite static patch that I didn't label, but which is over here. That's the static patch of perhaps a different observer who would be living here. So this killing vector field simply generates time translations for the particular observer who's on that black line at the edge. So that observer, it's called a static patch because to that observer, it looks like a time-independent spacetime. So let H be the generator of time translations. Now, in ordinary quantum field theory without gravity, we dissociate a Hilbert space H0 to de Sitter space. And then we dissociate a type 3 algebra A0 of operators in the static patch that acts on it. And if you ignore gravity, you'd say that the algebra of observables for someone who can only see what's happening in the static patch is A0. And it's a type 3 algebra, so we couldn't make sense of its entropy. It's a type 3 algebra because in ordinary field theory, the entropy of a region is always a type 3. However, in a closed universe, the isometries have to be treated as constraints in gravity. This is not true in quantum field theory. This is true with gravity. This is going to be the difference. I told you that gravity is going to change the picture, and the reason it will change the picture is that with gravity, the isometries become constraints. So the static patch has one important isometry, which is the time translations. And we have to treat time translations as constraints. That means we should replace A0 by the invariant subalgebra, the subalgebra of operators A0 that commute with H, which I denote as A0 with a superscript H, where the superscript means H invariant. But that doesn't work. People who work on operator algebras will tell us that in this problem, the modular automorphism group acts ergodically, which is a fancy way to say that the invariant subalgebra of A0 is trivial. It consists only of the complex scalars. So in ordinary quantum field theory, we can't impose time translations as a constraint. Well, okay, with or without, okay. We can't impose time translations as a constraint. We'd conclude that there's nothing to observe in ordinary quantum field theory. Oh, sorry. We conclude that there aren't any observables in the static patch because there are no H invariant operators. I tangled that up, but I stated it correctly last time, so I hope I was clear. The only way to get a reasonable answer is to include the observer in the analysis, which is something people have speculated about for a long time, that in gravity, the observer should be part of the system under the discussion. And now we're about to need it. As a minimal model of the observer, we assume that the observer at least has a clock, and we'll write little x for the Hamiltonian of the clock. The observer, of course, might have degrees of freedom other than a clock, but a minimal model where the observer has nothing but a clock measured by a single operator x will be enough. It's physically reasonable to assume that the observer's energy is bounded below by 0, so we will assume that x is non-negative. So the effect of including the observer is to modify the Hilbert space by replacing what would have been otherwise. Sorry, this is including the observer, but without the constraint. This is the effect of the observer without the constraint. Would be to add 1 degree of freedom in the Hilbert space, replace the Hilbert space by H tensored L2 of R plus. The algebra is likewise extended from A0 to what I'll call A1. A1 is A0 tensored with all operators that act on the clock. So the clock has a Hilbert space L2 of R plus, and we'll model the observer by assuming that the observer can manipulate the clock in any desired fashion. So now our algebra is A0 tensored with the algebra, the type 1 algebra, of all all operators that act on the clock. Finally, we have to impose the constraints. The constraint operator becomes the total Hamiltonian of the quantum fields plus the observer. So in other words, we said that the Hamiltonian of the observer was x. So this is H of the quantum fields plus x is the constraint operator. The correct algebra of observables, taking into account the presence of the observer, is the H hat invariant part, not of the original algebra, but of the extended algebra, including the observer's operators. So this is the correct algebra of observables for an observer living in de Sitter space and observing the static patch. Essentially, by what's called Takasaki duality, this algebra is of type 2-1, which means there's a notion of density matrix and entropy. And also, because the algebra is of type 2-1 rather than type 2 infinity, there's a state of maximum entropy. The black hole does not have a state of maximum entropy because the black hole mass could grow and then the entropy would go up. So for the black hole, we got an algebra of type 2 infinity, but for de Sitter space, we got an algebra of type 2-1, which reflects the fact that de Sitter space has a state of maximum entropy, which is the natural de Sitter state, sometimes called the Bunch-Davies state, although actually investigated by prior authors. The density matrix of the maximum entropy state in the type 1 algebra is simply rho equals 1. That state has a flat entanglement in spectrum, as first predicted based on a Euclidean path integral by these authors here. So flat entanglement spectrum means that all the Rényi entropies are also maximal. Again, a variety of facts known from gravity can be recovered from the algebra. Now, I should stress something I haven't had time to explain, that entropy defined this way is really renormalized entropy. In passing to the infinite system of qubits to define the type 3 algebra that then became type 2 because of gravity, we've removed an infinite entanglement entropy in a sense. So what we're discussing are renormalized entropies, which physically are defined up to overall additive constants independent of the state. So entropy, as I've defined it, is analogous to entropy in classical physics, which, remember, was defined up to an additive constant by formulas like this one. So the first law defines entropy up to an additive constant. And I gave also previously a more microscopic explanation of why classically entropy is defined up to an additive constant that involved the formula rho log rho. In classical physics, there's no way to fix the constant. And likewise, when we describe the black hole or de Sitter space by a type 2 algebra, we only understand entropy up to an additive constant. To conclude, we've learned that at the level of semi-classical gravity, we can define an algebra A such that the generalized entropy in the presence of a black hole or cosmological horizon actually is the entropy of a state of the algebra. And to answer some question about the nature of black hole entropy, it certainly answers the question, it gives a slightly abstract answer to the question of why this formula is better defined than either term separately. This algebra doesn't have pure states, so at this level, there's, for example, no notion of a black hole microstate. But nonetheless, there is a notion of entropy, and to answer some questions about black hole entropy. Thank you so much for your patience, and sorry for going a bit over.
Thank you so much. Thank you for the very nice talk. Yeah, so the floor is now open for questions. So because we have many participants, then please raise your hand first if you have a question. And maybe let me start with the seminar room in Göttingen. Do you have questions there?
I see a few
Probably
questions.
not. Yeah, so let's carry on with the questions from the Zoom. So please, the first person I see is Angaren. Please go ahead.
Hi, thank you for the great talk. I just wanted to get some clarification regarding your point about Bunch-Davies being a maximum entropy state. Is this a statement of QFT and curved space-time, so like the Hartle-Hawking state in the infinite past having a Bunch-Davies vacuum initial condition, or is that a quantum gravity statement, so it's the full Wheeler-DeWitt state?
Well, it's meant to be a quantum gravity state. Now, the assertion that the Bunch-Davies state has the maximum possible entropy has been made before, based on considerations of gravity. I wouldn't want to claim it was proved before, but it was believed before by various researchers, and different people gave different reasons. But the original reason, which goes back, I believe, to Gibbons and Hawking, was to consider a black hole in de Sitter space. And then the entropy was defined as the sum of the entropies of the cosmological horizon plus the black hole horizon. And they observed that that sum is always less than the cosmological horizon area for the Bunch-Davies state. So at least for the case where instead of de Sitter space, you consider a black hole in de Sitter space, that reduces the entropy. Later physicists have generally suspected, though I wouldn't want to claim it was proved, that the Bunch-Davies state had the maximum possible entropy of any state in de Sitter space. Regardless of the extent to which you think it was convincingly shown before, it's definitely a true fact in the context of what I'm telling you now, because we got a type 2-1 algebra describing any state in the static patch. And it is simply a fact, as originally pointed out by Siegel in 1960, that for a type 2-1 algebra, there's a state of maximum entropy, which we assert matches the Bunch-Davies state.
Okay, no, thank you very much.
Sure.
Thank you. I see that Hal has a question. Go ahead, Hal.
Yes, okay. Yeah, thank you very much. It was a great talk. So I want to ask a naive question. So what is essential about gravity in this story? So in other words, can we imagine something else playing the same role of converting type 3 to type 2 in different contexts, like in condensed matter system, in infinite volume limit?
Well, let me tell you what I believe is a condensed matter analog, but I don't know how interesting it is. I've actually not discussed this with any condensed matter physicists, but I wondered if you take the infinite volume limit, you get a type 3 algebra.
Yes.
But if you work asymptotically in your infinite volume, don't actually take the volume to be infinite, but do a kind of asymptotic expansion near v equals infinity. I think it will make sense to get a type 2 infinity algebra in that asymptotic expansion.
But there's nothing like gravity sitting
No.
there.
No, but you see, I didn't, in my, okay, in my actual paper on the type 2 infinity algebra, I was in anti-de Sitter space, and I had a more technical argument that involved the large n limit. And there's a close analogy between the large n limit and the large volume limit. So, see, for finite volume, the algebra in thermodynamics, in system mechanics, is type 1. In infinite volume, it's a type 3. Well, I believe if you work not at infinite volume, but asymptotically near infinite volume, in a certain sense, you'll see a type 2 infinity algebra. Well, since you're working asymptotically, it won't really be a type 2 infinity algebra over C. Sorry. It'll be more like working asymptotically over C augmented by a parameter, which you can think of as e to the minus v, or maybe 1 over v. I don't know technically the best way to do it. But I don't know if it's useful for condensed matter or quantum statistical mechanics. But I do think it makes a lot of sense to try to define an asymptotic type 2 infinity algebra near infinite volume, by not quite taking the infinite volume limit. That would be analogous to what I actually did in my paper, which was a little different from the way I explained. Unfortunately, I cut some corners in the way I explained it, but the reason I didn't want to follow the explanation in the paper is that requires a whole nother background about anti-de Sitter space and ADS-CFT duality. And there simply wasn't time to do that, as well as explaining the Hawking effect and what is a type 3 algebra. So therefore, I didn't actually follow the paper. If you look at the paper, you'll see a technical argument that's different from the way I explained it. Well, it's easier to think of the technical argument because it requires less thinking. I just did, in the paper, I just did a straightforward expansion in 1 over n. To make carefully the argument I tried to sketch, which was for the asymptotically flat case, requires thinking very carefully in a way that, well, what I explained was too compressed to satisfy me, actually. In the paper, I want to explain, in the paper that isn't written yet, I want to explain carefully the argument I tried to sketch in the talk.
Okay, thank you very much.
Sure.
Thank you, Hal. Next question, Wei Guang.
Thank you. You mentioned that in these stories, we will get a type 2 algebras and there's no notion of microstates. And I heard that there are some programs that we can counting in some string theories about the microstate explanations of the black hole entropies.
Yes.
Does it mean that in that situations, we have type 1 algebras?
Sort of, but that situation is at 0 temperature. So when the microstates are counted, those are extremal black holes, which are at 0 temperature.
Yeah.
And at 0 temperature, it makes sense to have a type 1 algebra.
Only 0 temperatures make sense for type 1.
Yes. Yes. Well, it's certainly not known how to define a type 1 algebra at non-zero temperature. I would personally conjecture, my personal suspicion is that black holes don't really have microstates, except in the 0 temperature case where they were counted. When I say that, I mean the following. A technical statement would be in the context of the ADS-CFT duality that I didn't describe today, but trying to avoid technical statements. A physical system consisting of a black hole and everything outside it certainly has quantum microstates.
Yeah.
If you form the black hole by letting tables and chairs collapse, you started in a pure state, and you should still be in a pure state if you include all the outgoing stuff. However, a description where you can actually see quantum microstates, I believe, is in tension with a description where causality is a clear concept. When you call something a black hole, you're invoking a classical notion of causality, which I believe is valid when gravity is treated asymptotic in an asymptotic sense, but possibly not if gravity is treated exactly. So I personally suspect that part of the reason for a problem in understanding quantum black holes is that you don't simultaneously have causality as a sharp notion and also microstates as a sharp notion. So I actually suspect, although this goes way beyond what has been established either in any of the papers, including the papers not written yet, I actually suspect that the type 2 answer is the best possible for a black hole of positive temperature.
Okay. Well,
But I
thank
don't
you.
know. I'm just speculating there. I'm going beyond what we know, even what isn't written.
Yeah, thank you.
Sure.
Thank you for your question. Next, we have Rishi. Please go ahead.
Hi. I have a few questions actually, but let me go one by one. So how in a type 2 infinity algebra, you have an undetermined constant in the entropy, correct?
That's right.
How did you fix that constant to be the area?
We didn't. We really only see area changes. So
Okay.
Aaron Wall had a beautiful formula. Sorry. Well, we made contact with Aaron Wall's formula. So Aaron Wall had a formula that the generalized entropy was the area measured at infinity minus the relative entropy on the horizon between the state of interest, the state of interest, and the Hawking state. So we made contact with that formula, except that in our computation, what plays the role of A infinity differs from A infinity by an arbitrary constant. If you like, we measure the entropy of all states relative to thermal equilibrium at the temperature T that was assumed in starting the discussion. So we make contact with a version of Aaron Wall's formula. The full story is a little bit too long, but okay. Remember, we added one operator. So the Hawking state defined just for the bulk is missing that operator, but we can extend it by multiplying by a function of this new thing. That gives an extended state. For this state, I gave an exact density matrix in my paper. Now, what I didn't understand, but what was shown mostly by my co-author Pennington more recently, is you could take any state tensored with G. You should assume G is slowly varying. You have to assume G is slowly varying, or else the state doesn't have a semi-classical interpretation. So this is really for any semi-classical state. And then you can get an approximate density matrix. So Jeff wrote an approximate density matrix for any semi-classical state. And then showed that minus trace rho log rho agreed with Aaron Wall's version of the formula, essentially up to a constant, which you can think of as the area at thermal equilibrium. I think that's the best I can explain it now, I'm afraid. There will be a paper, but not yet. I hope that's at least somewhat clarifying.
I see. Thank you. If I may ask one more, or should I just go back?
No, go ahead.
Yeah, maybe let's give other people a chance, and then we'll come back to you if that's okay.
Sure.
So Henning Reijden, do you have a question?
Yeah, so hi, Edward. Thank you very much for this interesting talk. If I understand you correctly, then when you talked about quantum fields, you had in mind gravitational degrees of freedom, like Riemann tensor.
Yes.
And in the de Sitter case, you had to add a clock by hand.
What it would mean with the, okay, yes, go ahead. Ask your question, then I'll answer it.
Yeah, but of course, our universe is full of matter and galaxies and quantum fields of all sorts which are not gravitational. And and naively, one may think of a tensor product of a gravitational and a matter Hilbert space. And these the matter state is, I mean, the total state is highly entangled between matter and gravity. So
that's part of the discussion. For brevity, I only talked about constructing H naught from gravity, but of course, H naught was made from gravity. H naught was the naive Hilbert space of the low energy effective field theory, ignoring some of the subtleties of gravity. It included matter, and everything is completely entangled. That's all. Everything you've said is part of the discussion. But the important thing is that the H naught you would construct by simply treating the gravitational field as a spin-2 field in a fixed background isn't quite correct. It needs to be corrected by adding one mode and one constraint. So
yeah, but my impression was that you did not discuss the entanglement between these two tensor factors.
well, I didn't discuss it explicitly, but the discussion was sufficiently general that it encompassed an arbitrary state in this tensor product Hilbert space. So believe me, all our discussion and formulas entirely include that.
Okay, okay.
As for the clock, you see, what does it mean to say that there's a clock in the static patch? What it really means is that we're not going to discuss an arbitrary possible state of the system. We're going to stipulate that there is an observer present. The observer is part of what was described by H0 matter. The observer is in here. I didn't make it explicit. We're working in what people in what quantum computing would call a code subspace of states that are stipulated to have an observer. In the real world, it could be the Milky Way galaxy was our clock. We could say that we're going to study, the real world is approximately in de Sitter space. I said that the observer at least had a clock, but could have more stuff. The observer could be the whole Milky Way galaxy. Then we're studying states in the static patch that include the Milky Way galaxy. That's not the whole Hilbert space, it's a subspace. So I defined an algebra. There were a few steps in defining the algebra, but I ultimately defined an algebra, which was sort of a bulk algebra, a naive bulk algebra, tensored with an algebra of the observer, and then you had to impose the correct constraints. But the algebra I defined didn't make sense in all states. It only made sense in this. If the Milky Way was used as the clock, then this algebra is only defined for states that do contain the Milky Way. But everything you're saying is part of the discussion, but in view of time, I had to cut an awful lot of corners.
Yeah, okay, okay. Yes, thank you very much.
Sure.
Thank you, Henrik. Jean-Michel?
Hi, so I have a question which might be a little bit marginal to the main topic of your talk. It's about this observer and the clock which realizes it. So it has a Hamiltonian, which is just multiplication by x on x non-negative, and so it's bounded below.
Yes.
And the time observable, I suppose, is supposed to be the conjugate variable. Now, there is this usual objection to a time observable in quantum mechanics, which should increase at the rate 1 and therefore have a commutator 1 with the Hamiltonian that forbids a Hamiltonian that is bounded below. Is that an issue of any sort?
Well, it means that the clock can't work as a clock for an infinite amount of time. It can only work as a clock for a large amount of time. So you can make a very good clock. For example, in the example where the observer is the Milky Way galaxy, with the resources of the Milky Way galaxy, we could collect some radioactive atoms and build a clock that will work very well over 10 to the 20 or more years, using a lifetime radioactive atom with a lifetime of 10 to the 20 years, and those actually exist. But it won't work well forever. So what you've said proves that a clock can't work for all times. In the example of the real world, we really want a clock that works for much longer than 10 to the 11 years, because 10 to the 11 years is the time scale in which the universe behaves like de Sitter space. And I believe that the resources of the real world let us build a clock that will work for much longer than 10 to the 11 years, but not forever. So I think the discussion is realistic.
Thank you.
You didn't ask another embarrassing question, which is that when I took the Hamiltonian to be X, that meant the Hamiltonian had a continuous spectrum, which is a little bit unphysical. I don't know the best answer to that question, and maybe I shouldn't have volunteered the question since you didn't ask it, and I don't know a good answer, a simple-minded answer, but I'm not sure whether I should be satisfied or not with this answer. I'm still thinking about it. Is that if I had taken the Hamiltonian to be X plus G times, X plus Newton's constant, big G, times P squared, that has a discrete spectrum and would have been just as good for everything I said if you. Unfortunately, it makes the arguments much longer. So it has a discrete spectrum and you can argue it's just as good, but you have to work much harder. So shutting your eyes and allowing the continuous spectrum, see, we were expanding around G equals 0. So near G equals 0, you don't see this correction. That's why this is just as good. Shutting your eyes and taking the Hamiltonian to be X is extremely simple and gives a sensible answer for all questions. But there are some things I worry about.
Thank you. So we can probably cycle back to Rishi. You can ask another question.
Hi. So the question I wanted to ask is, so presumably the type 2-1 algebra in the de Sitter case corresponds to the fact that if you add matter, the cosmic horizon shrinks, right?
That's the type 2-1. That's the fact
Yeah.
that it's type 2-1. Yes.
Yeah, great. So what happens if you add a black hole in the static patch? Well, it's not a static patch anymore, but what happens if you act with so much energy that you get a black hole on top
Well,
of the
this
horizon?
was first studied by Hawking, Gibbons and Hawking. And I think it was first by Gibbons. First of all, it can be static. So the observer could have been a black hole in my discussion.
Mm-hmm.
So the black hole, when the same world line as the observer, would preserve the fact that it's static. And then there's a simple solution, which is called the de Sitter-Schwarzschild solution. And it's got a black hole horizon and a de Sitter horizon. I need to look this up, but I think it was Gibbons and Hawking who showed that the sum of the two areas is less than the de Sitter area.
Right.
And
I was asking, yeah.
let me
Sorry,
finish for everybody else. And that led to the belief, so that led to the statement that including a black hole lowers the total entropy. And it led to a belief that the pure de Sitter vacuum has the maximum possible entropy.
I see. So,
And we have an algebraic explanation for that in terms of the type 2-1 algebra.
okay. Thank you. So to be clear, the type 2-1 algebra describes the region between the black hole horizon and the cosmic horizon, is it?
Yes. Well, if you're an optimist and you, okay, it depends on what we want to assume is known. If you think that in principle, a black hole, you see, as I said before in answering one of the questions, a black hole and all the stuff outside it, we think in principle is described by a type 1 algebra. If you're in asymptotic Minkowski space, but we don't understand that. In the same sense, I could claim there's still a type 2-1 algebra. If you had a complete understanding of the black hole horizon, then you would, but you can't see beyond the de Sitter horizon. You would go back to having a type 2-1 algebra.
Okay, thank you.
It really is going to depend on what you assume is known.
Thanks a lot.
Sure.
Thank you. Jörg, do you have a question?
Yeah, I have a question. What do you mean by observer? You just add some degrees of freedom, but obviously, 200,000 years ago, there were no observers. So I don't like this notion to appear in such a talk.
Well, I explained, the observer could be the Milky Way galaxy. So in other words, I defined an algebra that isn't well defined for all conceivable states in de Sitter space,
Yes.
but it's defined in a subspace of states that contain the Milky Way galaxy.
Mm-hmm.
So it's analogous to what people in quantum computing call a code subspace. So certain operations aren't defined in the whole Hilbert space, but only in a subspace.
Yes.
So we first tried to define an algebra that made sense for all states. So we had this algebra A0, and then we tried to take this sub-algebra of constraints. There weren't any meaningful operators.
Yes.
So in the abstract, you can't define anything in the static patch. However, if you know that the static patch contains the Milky Way galaxy, then you're in a subspace of states. And in that subspace of states, you can define an algebra of observables. We didn't need the whole Milky Way galaxy. It was enough to have a clock in the static patch. And even a very simple model of the clock was enough.
Yeah.
As I said when I introduced the clock, the minimal model where the observer was characterized only by this one operator X was enough. But of course, a realistic observer would have much more stuff.
Mm-hmm.
Mm-hmm.
Yeah. Okay.
Okay. Yeah, so maybe let me throw one question of my own as well. So you mentioned that in the paper you're using ADS-CFT correspondence to prove things, but in the talk you used a bit of a different argument. So is this ADS-CFT correspondence a crucial part of this discussion, or it's just a technical simplification? I mean, can one fully make the argument precise the way you did it in the talk?
Well, I believe the answer to that is yes. And I'm very much hoping that the paper will contain a clear explanation of the argument in Minkowski space, asymptotic flat space. I think it's trickier. So technically, there are many things about black hole thermodynamics which people discovered using ADS as a technical tool or convenience, but which don't depend on it. Some are known not to depend on it. Some are still not fully known. And I believe that the type 2 nature of the algebra in the field of the black hole is general, but with the ADS machinery, I really didn't have to understand very much. I just expanded 1 over n.
Right.
And force correction. I should have perhaps mentioned that my inspiration was a paper by Liu and Leuthäuser. They took the strict large n limit. I might be misspelling Leuthäuser wrong. Anyway, they took the strict large n limit, so I corrected what they did by including a 1 over n correction, and found that they had constructed a type 3 algebra. I found that the 1 over n correction turns it into type 2. I only had to do a simple perturbative calculation. To state the argument in a way that's more general, you have to think more carefully, which I was trying to do in the talk, and I hope to write it up carefully in a paper. But I think it should still work, but you have to think more. It's less easy to understand.
And this, well, the type 2 result, this is really, you think that this is related to introducing the gravity in this semi-classical approximation, is that right? I mean, would you expect, and this is a very vague question, what would you expect would happen if you included quantum gravity effects more fully? Like what sort of algebras do you imagine would be relevant for the full theory of quantum gravity, or something more in that direction?
Well, I imagine that a black hole in asymptotically flat space-time is described by a Hilbert space that acts irreducibly. So they're the type 1 algebra in principle. What I'm not sure about, though, is whether you can, in a precise fashion, say it's a black hole while also having a type 1 algebra. Because I believe there is a tension between having microstates, in other words, pure states of a type 1 algebra, and also being able to talk about classical causality.
Right, yeah.
Although there's a type 1 algebra, I'm not sure that, although I suspect there's a type 1 algebra, I'm not sure there's a type 1 algebra together with a precise notion of causality in the classical sense. So I think it's conceivable that type 2 is the best you have if you also want to have causality.
If you want to have both.
Causality as we understand it classically. I don't know, though. That's a speculation.
Okay, thank you. There are 2 more questions, but I think maybe let's finish this sort of official part of the Q&A session and thank Edward again.
Well, thank you for the invitation and for all the questions.
And we can